Hi everyone, welcome to the channel. I'm Zhibin Guo. So where do we begin? Honestly, chromatography can be a lot. It is a huge, complex world filled with messy peaks and endless calculations that can feel a bit overwhelming. But for us, and I'm sure for many of you, we can't get enough of it. There's something so cool about uncovering the hidden secrets of polymers and proteins, and that's exactly what we are exploring today. In this video, I'm excited to show you the BeSEC Series, our new light scattering detector for SEC and GPC. Whether you are a researcher chasing higher precision or just curious about the tech, this system is all about turning messy data into clear, easy answers. So let's jump right in and look at the world of light scattering. To begin our discussion, I would like to provide a brief introduction to the core concepts and the challenges we are addressing in modern polymers analysis. Before we go further into the tech, let's take a step back and ask, what exactly is a polymer? Simply put, a polymer or macromolecule is like a long chain. It's made up of many small repeating structural units all linked together by covalent bonds. Think of it as a necklace where each bit is a molecule. When you string them all together, you get something entirely new with unique properties. We see these everywhere in our daily lives, especially natural polymers. For example, look at the wool or silk in a cloth. One is made of keratin and the other of fibrin. They give us that soft, elastic, or lustrous feel we love. And then there's starch, which is just a long chain of glucose units, or natural rubber from cheese, which gives us that incredible stretch and flexibility. Even though these materials look and feel very different, they all share the same internal chain structure. Understanding these chains is the key to mastering material science, and that's where our measurement tools come into play. Now that we've looked at what nature gives us, let's talk about synthetic polymers. They are the man-made macromolecules that literally build our modern world. Depending on how those chains are put together, we can create materials with widely different properties. Take PE, polyethylene, for example. It's flexible, has low density, and resists corrosion, which is why you see it in everything from plastic bags to containers. Then there's PS, polystyrene. It's a lighter weight and easy to process, though it can be quite brittle. If we need something tougher, we turn to POM. This one is known for its high strength and wear resistance, making it perfect for high precision engineering parts. And finally, we have PMMA, which you might know as acrylic. It's prized for its optical grade transparency and high hardness, often used as a lightweight alternative to glass. As you can see, the diversity here is huge, but to make these materials perform correctly, we need to know their exact molecular weight and distribution. That brings us back to why precise measurement is so critical for innovation. So what exactly do we mean by molecular weight? Scientifically, it represents the average mass of our molecule compared to carbon-12. We measured this in a unit called the Dalton, where 1 Dalton equals 1 gram per mole. To give you some perspective on the scale we are talking about, a simple glucose molecule is only about 180 Daltons. A DNA base pair is around 650 Daltons. As we move into proteins like lysozyme or BSA, we are looking at 14 to 66 kilodaltons, and something like IgG can reach 150 kilodaltons. But why do these numbers matter so much? Because for polymers, molecular weight is the key to their strength, toughness, and elasticity. Unlike simple monomers, a polymer's real-world performance, like how it melts or when it breaks, is all determined by the length and distribution of its chains. It's a balancing act. If the molecular weight is too low, the material won't be strong enough. But if it's too high, the melt viscosity shoots up, making it too thick to process. We are always looking for that sweet spot to balance performance with processability. Here's the tricky part. Unlike simple molecules with a fixed formula, polymers are a mix of chains with different lengths. That's why we can't just look at a single average number. We have to understand the molecular weight distribution. Are there too many short chains making it brittle, or unusually long chains causing processing headaches? By measuring this distribution, we can truly optimize our materials and predict how they will behave in the real world. I would like to talk more about molecular weight parameters in this slide. First, there's Mn, the number average. Think of this as the simple arithmetic mean. It's very sensitive to the number of small molecules in your sample. Then we have Mw, the weight average. This is the one we use most often because it gives us more weight to the larger chains, making it a much better predictor of physical properties like thickness. Finally, there's Mz, the Z average, which is even more sensitive to the actual large molecules or aggregates. But the real magic happens when we look at the ratio of these numbers, known as polydispersity or PD. This tells us the distribution width. If your PD is close to 1, you have a monodispersed sample. This means your polymerization is well controlled, which is critical for precision materials like photoresist. On the other hand, a PD greater than 2 means you have a broad distribution. This often happens in free radical polymerization and can lead to performance instability. By understanding these parameters Mn, Nw, and Pd, you aren't just looking at random numbers, you are looking at the structural fingerprint of your material. We have covered the background. Let's take a close look at the SEC GBC system and how the various hardware components work together. Now let's talk about the engine behind these measurements. You've likely heard a few different names, GPC, SEC, and GFC. While they might sound different, they are essentially the same technique. What makes SEC truly unique compared to other methods is how it separates molecules. In most chromatography, separation happens because particles interact chemically with the stationary phase. They might stick together due to electrostatic forces or hydrophobic interactions. But in SEC, there's no chemical interaction. Separation is based purely on size. As you can see in the diagram, the column is packed with porous beads. Large molecules can fit into these pores, so they take the fast lane through the column voids and elute first. Small molecules, however, enter the pores and take a much longer winding path, which means they elute later. On the right, you can see the results on the chromatogram. The blue larger particles comes out early, while the red smaller ones appears much later. It's a simple process that allows us to sort complex mixtures by size alone, without the mess of chemical interference. Now that we understand the principle of separation, let's look at the actual hardware. A conventional SEC GBC system might look complex, but it follows a very logical flow. Everything starts with the mobile phase, which is the solvent that carries your sample through the system. To ensure the highest data quality, the solvent first passes through a degasser to remove any air bubbles, and then a pump maintains a constant, steady flow. Next, we have the injection stage. Using an autosampler syringe, the sample is pulled from the vial and loaded into the sample loop via the injection port. A 6-port valve that switches the flow, pushing your sample into the column. As we discussed, this is where the molecules are sorted by size. Finally, once the molecules exit the column, they pass through a concentration detector, typically an RI, refractive index, or UV-Vis detector. This tells us how much materials is coming out at any given time. So, how do conventional systems determine molecular weight? They rely on concentration detectors like RI or UV. The RI detector is often called a universal detector because it works for almost all polymers. The UV detector is more specialized. It's great for light-absorbing samples like proteins. However, here's the catch. These detectors can't see molecular weight directly. They only see concentrations. To get a weight, you have to perform a calibration. This involves running a series of polymer standards with known molecule molecular weights to create a calibration curve. As you can see in the graph on the right, we plot the retention volume against the known log MW. Then when we run an unknown sample, we look at the way it looks and calculate its molecular weight based on that curve. This gives us a relative molecular weight, which works, but it assumes your sample behaves exactly like the standards you used. But in the real world, relying on calibration curves has some serious drawbacks. First, it's time-consuming. You have to spend hours preparing and running standards before you even touch your actual sample. The bigger issue, though, is accuracy. Look at the figure on the right. Different polymers like polystyrene, polyisoprene, and polybutadiene all have unique hydrodynamic properties. This means even if two different polymers elute at the exact same time, they might have completely different molecular weights. If you don't have a standard that perfectly matches your sample, your results will be off. Plus, this method often overlooks critical structural details like branching or aggregation. And since column performance naturally decreases over time, your calibration curve can become out of date, leading to even more inconsistencies. Now that we've seen the limitations of traditional approach, let's look at how the light scattering detector fits into the picture. The front end remains the same. Mobile phase, degasser, and pump still handle the solvent delivery. Your sample is still injected via the syringe and 6-port vial onto the column for separation. The big change happens right after the column. Instead of going straight to a concentration detector, the flow first passes through the BeSEC. Because it's a non-destructive measurement, your sample then continues on to your existing RI or UV detector. By simply adding the BeSEC into your flow path, you've upgraded your entire system. You are no longer just getting the concentration data, you are now capturing real-time light scattering the signals. This allows you to calculate absolute molecular weight for every single slice of your pea. It's a seamless integration that turns your standard setup into an analytical powerhouse. This brings us to why the BeSEC series is a total game changer. If we compare to the conventional method, the differences are clear. While conventional systems give you a relative MW based on retention time, the BeSEC gives you absolute molecular weight directly via the Rayleigh equation. This means you can finally say goodbye to those tedious calibration curves. Your results are no longer tied to how long the sample stays in the column. But it's not just about speed, it's about data quality. BeSEC uses light scattering. It's very sensitive to trace aggregates that a standard RI detector would completely miss. You also get more structural information like the radius of gyration. Whether it's higher accuracy, better efficiency, or the ability to handle complex samples without standards, adding a light scattering detector like the BeSEC turns your SEC system into a precision tool. Let's get into the star of the show, the light scattering detector BeSEC. So what makes it stand out? First, it covers a massive molecular weight range from 1,000 daltons all the way up to 2 gigadaltons. We've equipped it with a high stability laser and a tiny 18 microliter sample volume to keep diffusion effects to an absolute minimum. Plus, the software is intuitive, giving you real-time analysis as you work. But the real win is the convenience. Since it measures absolute values, your results are no longer tied to illusion volume. It's also a plug-and-play solution, meaning it's compatible with any SEC or GPC systems you are already using. The BeSEC is a highly versatile inline detector that integrates seamlessly with third-party chromatography systems to deliver absolute molecular weight and distribution data. This slide shows the dual-angle design of the BeSEC system, which integrates a 90-degree RALS detector and a 7-degree LALS detector in a single optical bench. The 90-degree detector provides high sensitivity for smaller macromolecules because their light scattering is uniform in all directions. For larger molecules, the 7-degree detector is used to ensure high accuracy, because large molecules exhibit strong angular dependence in their scattering pattern. Measuring at 7 degrees allows the system to capture the true scattering intensity near the theoretical 0-degree limit without needing complex mathematical extrapolations. In addition to the detection angles, the BeSEC features a very small 18 microliter flow cell. This small internal volume is a significant advantage over many multi-angle systems because it reduces band broadening caused by sample diffusion, keeping your chromatography peaks sharp and precise. Furthermore, by combining the LALS data with the RALS signal, the system can generate a 2-point zoom plot. As you can see in the graph, the slope between these 2 points allows the software to perform a RG estimation. This means you get both a highly accurate molecular weight and a clear picture of the size of your sample in a single analysis. The absolute determination of molecular weight is governed by the Rayleigh equation, which relates scattering intensity to mass. In its full form, the equation includes a form factor to account for how light scatters at different angles. According to this theory, measuring scattering at exactly 0 degrees would be ideal because it simplifies the calculation entirely. At 0 degrees, the angular term becomes 0 and the form factor equals 1, allowing us to determine molecular weight directly. However, in a real-world instrument, detecting light at 0 degrees is impossible because the high-intensity instant laser would blind the detector. To solve this practical challenge, we use low-angle light scattering, or LALS. By measuring the signal at a very low angle, we can directly capture data that is close enough to 0 degrees to avoid the need for complex extrapolation. This approach provides a much more direct and reliable path to calculating absolute molecular weight. To understand the practical advantage of this design, let's look at how scattering intensity changes as molecular weight increases. At ultra-high molecular weights, reaching up to 10 to the 7th power daltons, the scattering signal at higher angles drops significantly due to the strong angular dependence. As shown in the graph, the intensity at a 90-degree angle falls to nearly 20% of its true value at the high end of the mass scale. The 7-degree measurement remains remarkably stable across the entire range. Even for the largest macromolecules, the difference between the scattering intensity at 7 degrees and the theoretical 0 degree is less than 2%. This makes the 7-degree detector a highly reliable substitute for 0-degree detection. By ensuring both accuracy and the robustness, the BeSEC with LALS provides the high-quality, consistent analysis required for even the most challenging polymer samples. Finally, with the technical principles established, we will explore the applications section to see how this BeSEC system performs in real-world laboratory scenarios. Versatility of the BeSEC system is demonstrated by its wide range of applications across 3 major sectors. In the field of synthetic polymers, the system is ideal for characterizing common industrial materials such as polystyrene, PVC, and polycarbonate, providing the precise molecular weight distributions necessary for quality control and material development. Moving into natural polymers, the BeSEC effectively analyzes complex polysaccharides like hyaluronic acid, heparin, and chitosan. These substances often have high molecular weights and complicated structures, making the direct measurement capability of our LALS detectors particularly valuable. Finally, the system is highly effective for proteins and biologics, including monoclonal antibodies and serum albumin. By accurately measuring these delicate samples, researchers can monitor protein aggregation and stability, which are critical factors in pharmaceutical research and biotechnology. To see these principles in action, let's look at an application example involving ABS resin. This material is a widely used polymer in industries like automotive and electronics. The performance of ABS is heavily determined by its molecular weight, so having accurate data is essential for choosing the right grade for a specific task. For instance, Low molecular weight ABS offers excellent fluidity, making it ideal for processing small and complex parts. However, it often comes with a trade-off in terms of lower strength and heat resistance. On the other hand, high molecular weight ABS provides much better mechanical properties and impact resistance, but it is more difficult to process due to poor fluidity. In this example, the BeSEC system used a GPC column with THF to analyze the sample. By combining the LALS and RALS signals, we can clearly see the different fractions within the resin and the difference among 4 samples. The measurement results table show that the absolute values for Mn, Mw, and Mz, as well as the polydispersity. Our next case study focuses on polycarbonate, a material valued for its exceptional strength and clarity. The physical properties of PC vary significantly within its chain length. For example, low molecular weight PC is characterized by its excellent fluidity and processing performance, making it a preferred choice for small injection molded parts or as an additive to improve the flow of other polymers. In contrast, medium molecular weight PC offers a balanced set of properties, providing the necessary strength and weatherability for demanding applications like automotive interiors and electronics. Looking at the experimental data on this slide, we analyzed 2 different samples, PC number 1 and PC number 2, using a GPC column. While the peak molecular weight of both samples appears quite similar, a closer look at the molecular weight distributions reveals a key difference. As shown in the chromatograms and the measurement results, PC number 2 contains a higher proportion of higher molecular weight components. This difference is critical for manufacturers to understand, as these heavier chains can significantly affect the fluid properties and the melt behavior during production, even when the average molecular weight seems constant. Moving into the realm of natural polymers, let's examine carbocarrageenan. This sulfated polysaccharide is a vital functional ingredient whose performance is entirely determined by its molecular weight. For instance, gel strength is directly linked to chain length. A higher molecular weight results in stronger, more elastic gels, whereas a low molecular weight can significantly compromise the material's mechanical stability. Similarly, the viscosity and thickening power of the solution are molecular weight dependent, meaning manufacturers must strike a precise balance to ensure both effective performance and ease of processing. Beyond texture, the functional performance of carrageenan in products such as film forming ability and water retention is also a reflection of its molecular weight. In the analysis shown here, by leveraging the BeSEC system, we obtained an absolute molecular weight of around 260 kilodaltons. This precise characterization allows formulators to guarantee that every batch meets the required quality standards. This slide shows another application example. Polysaccharides are vital to biological function and show a wide range of bioactivities, but their complex, high molecular weight structures hinder structural activity relationship studies. Ultrasound degradation offers an efficient, eco-friendly way to cleave glycosidic bonds, reducing molecular weight. This improves solubility and processability and can enhance bioactivity by exposing previously inaccessible functional groups. If we look at the experimental data on this slide, we can see the dramatic impact of 40-minute ultrasound treatment on our polysaccharide sample. Before treatment, the BeSEC system measured an absolute molecular weight of over 1 million daltons with a radius of gyration of 77 nanometers. After degradation, the molecular weight dropped to approximately 264 kilodaltons, and the size decreased to 21.5 nanometers. The chromatogram clearly shows the peak shifting to a later retention volume, providing a precise visual of how the degradation process transforms the physical properties of the polymer. This application is related to the biopharmaceutical sector, particularly for characterizing human serum albumin. The primary and the most desirable form of HSA is the monomer, which has a molecular weight of around 66.5 kilodaltons. Under normal conditions, this monomeric form is dominant and is preferred for therapeutic use due to its high solubility and low immunogenicity. However, during storage or processing, HSA can form oligomers, such as dimers, trimers, and tetramers, through disulfide or non-covalent interactions, which can affect its pharmacokinetics. The most significant concern in biologics, however, is the formation of larger aggregates. These aggregates not only decrease bioavailability, but also trigger dangerous immune responses in patients. As shown in the data on this slide, we analyzed 2 different HSA samples. By utilizing the absolute measurement power of the LALS detector, we can precisely quantify the content of each fraction. In the table, peak area analysis indicates that the monomer accounts for roughly 77% of the total protein in both HSA samples, while a significant fraction exists in aggregated forms. This level of detail is essential for the strict control required in pharmaceutical formulations to ensure both safety and efficacy. To conclude this application series, we turn to IgG. The functional reference is the monomer, about 150 kilodaltons, with the characteristic Y-shaped structure. This form is preferred in therapeutic formulations because it offers the highest stability and consistent biological activity. Under environmental stress or during long-term storage, IgG can form oligomers such as dimers and trimers, which may alter antigen bonding and reduce predictability. As with HSA, IgG aggregates raise serious safety concerns due to their potential to trigger immunogenetic responses. The results shown here highlight the capability of the BeSEC system in resolving such complex mixtures. The analysis clearly identifies the monomer as the main component at 76%, while accurately determining the absolute molecular weight of the dimer at about 295 kilodaltons and the trimer at 450 kilodaltons. In this study, the BeSEC system demonstrates the static light scattering can effectively resolve monomer, dimer, and higher-order species and quantify their content. That brings us to the end of today's presentation. We have seen how this technique helps address real questions, from material performance to biomolecule safety and quality. With straightforward integration and direct absolute molecular weight results, BeSEC is a reliable tool you can use with confidence in everyday work. Thank you for watching.